exponential distribution. So exponential distribution captures amount of time until some specific event occurs. So it is used for that kind of situation where how much time passes before what you are interested in occurs. And another one like important property of exponential distribution is memoryless property. It forgets what happened in the past. For example, if a bulb has not failed for 3 years, so when it is going to fail next will not be impacted by the fact that it has already working for 3 years. Or a TV set, if it has been working for like 5 years, it is going to forget that. There are situations where you can use exponential distribution, and that important property is it is memoryless. So amount of time until some specific event occurs. So it could be like time between your next Instagram notification. So you get a notification, and then when you get a next one, if somebody captures that data or Facebook captures that data will be modeled using exponential distribution. It could be time until your phone battery dies, or it could be waiting time for the next text message. The probability is given by f of x equals, so this symbol you have seen earlier also, this stands for mu. It's a Greek alphabet which basically used for representing mean. So what is mu? Mu is average waiting time. So there are many business applications where waiting time is an important aspect, like how many checkout station you should open at a given time. So if you have 12, whether you should open 3 or only 2 or all 12, or like how much time a customer has to wait in a queue. When we are using exponential distribution, there is another important number we are interested in. We represent that by m, which is 1 divided by mu. M is 1 over mu. And this is called decay parameter. So we'll see some examples. And one important property of exponential distribution is that mean is equal to mu is equal to standard deviation. Both of them are equal. Mean and standard deviation both are mu. If you create a picture similar to what we did earlier, if you have some random variable x of interest and you have f of x on the y-axis, let's say we start here and then it keeps on decreasing. So this number that you see is the maximum probability, the highest probability, max value on y-axis. And that number is your m, which is 1 over mu. So that is the decay parameter, which is the maximum probability captured on y-axis. So the only thing you have to be careful about when you are doing all your calculations, you have to be careful about whether you are working with mu or m, because one is 1 over the other, and sometimes if you are not careful where you have to use like m, instead of that if you use 1 by m, so your values will be very different. What is the probability that x is less than some small value x? P for probability, exp for exponential, and then x, and then 1 over mu. So it is 1 over mu or m, which is your decay parameter. If you are interested in the right tail, what is the probability of x more than x? Same idea. We are not interested in lower tail, which is the default. It is default here, that's why we don't have to write. Even if you write lower comma, lower tail equals true, you get the same answer. But because that's a default, we don't have to write. And then for pth percentile, so quantile exp, and you put this p value 1 over mu. So those are your R functions all at one place for easy reference. Number 84. So now when you read these problems, be careful about m and 1 over mu, because in the problem it will not tell you are we talking about mu or m sometimes. Suppose that useful life of a particular car battery measured in months decays with parameter 0.025. So here it is clearly telling you that maximum probability value on exponential distribution. We are interested in life of the battery. Define the random variable x. So one number that we are given is 0.025. So first let me write down what is given. So we are given the decay parameter, which is m, or also 1 over mu. So this is 0.025. Essentially, if we write x follows exponential distribution with m equals 0.025. So this is how we can write. Define the random variable x for a. So what will be random variable x? Yeah.
Is it how many months the battery lasts?
Number of months the particular car battery will last. Yeah, so that will be B. Is x continuous or discrete?
Continuous.
Continuous, yeah. So it's a continuous variable. Yeah, I'm just testing you.
I'm sorry.
No. Okay, C. C is on an average, how long would you expect car battery to last? Question itself is telling you what it is asking, average. So how do you find average for exponential distribution or mean for exponential distribution? Anyone want to try that? We know that the decay parameter is 0.025. If decay parameter is 0.025, what is the average? 1 divided by that number, 0.025. So average or mean, you know that it is captured as mu, and because you have decay parameter as 0.025, so it will be 1 divided by 0.025. That will come to about 40 months. So these batteries last on an average 40 months. Any idea what is the standard deviation of these battery lives? Same thing, because mu and sigma standard deviation for exponential distribution is same. D is, again, on average, how long would you expect 9 car batteries to last if they are used one after another? So you start with 1, 2, 3, up to 9. How do we find that?
So you just
Multiply by 9. 9 batteries, each last 40 times, so 9 batteries will last 360 months. E, probability that x is more than 36. So you have exponential distribution, something like this, and this number is 0.025, and this is f of x, and 36, let's say somewhere here, and we are interested in this area. P, exp, 36, and then what should I put? What is the number I should use after 36? Yeah.
Would it be 40 is the mean?
Average is 40, but you see, we always use 1 over average, or that's the decay factor. So 1 over average is 0.025. So this is the number that we use, 0.025. And because it is in the right tail, we say lower dot tail is equal to false. So once you plug in, you get 0.4066. F. So 70% of batteries last at least how long? If I have to make this picture, you have random variable X, you have the probabilities, and you have this distribution shape. So somewhere 70% of the batteries last at least how long? So area to the left or to the right? Because at least. So it at least means that much or more. At most means that much or less. So if I say I want to get in exam at least 90%, it means 90, 91, 92, up to 100. So it is to the right, right? So at least means that is minimum, but it could be more. The line that you have and the area that we are talking about is like this is 0.7. We are interested in this value and then 0.025, but then you can say lower dot tail equals false, 14.3 months. Relationship between Poisson and exponential. And if you have, let's say, in terms of time, maybe number of people who walk into a store, somebody is capturing that. So there may be one person, second person, third person, and so on, in terms of time. And if you are measuring this time, like time between two customers that arrive at a store, so if you model that using a random variable X, time between two customers, so that's going to be a situation where you can use exponential, which means that a lot of customers maybe walk back to back into a store. There may not be much time gap, so you have like a higher probability for lower values. But then there could be like times when it's not a peak time or very few customers come. So the tail will go longer on the right side. So probabilities are going to reduce, continuously reduce. So that is an exponential pattern. But in case same data, if you are only looking at a random variable X and counting people, like in a given time interval, how many customers walk into a store? So if your focus is entirely on number of customers, where your values of X could be 0, 1, 2, 3, and so on. So that's what we have called earlier a Poisson situation. Same data, same information, depending on how you are collecting, whether you are collecting time between two events or just number of events, can become Poisson or exponential. So one example of this is try it 5.9. So in a small city, number of auto accidents occur with the Poisson distribution, average of 3 per week, 3 accidents per week. So you are counting numbers, 3 per week. A, calculate the probability that there are at most 2 accidents in any given week. So at most means 2 or less. So this is part A. So we are interested in what is the probability that X is less than equal to 2. in this problem we are given that x follows Poisson distribution with mu equals 3 accidents per week. So that's a historical data and that's the average. So using that, we can apply Poisson distribution and use this function P, P-O-I-S, so less than 2 and mu is 3. So it should come to 0.423. Now, connection of this situation to exponential. If you look at part B, what is the probability that there is at least 2 weeks between any two accidents? So now we are talking about time interval, at least 2 weeks between any two accidents. So time between two events or two accidents. So then it becomes exponential distribution. Obviously, we are interested in what is the probability that x is. I'm simply writing greater than because greater than equal to and greater than for continuous distribution is same. Because probability at any single point is 0 for continuous distributions. So what is the probability that x is more than 2? Now for this, I can make a picture of exponential. So you have this random variable x, number of weeks between two accidents. So that is x, fx, and then you have probabilities going down. And let's say somewhere here you have 2. So the idea is figuring out what is this probability. So for exponential distribution, we need to know mu or the decay factor. Mu for exponential is 1 by 3. If there are 3 accidents per week, then you take reciprocal of that. For exponential distribution, it becomes 1 by 3. It takes 1 by 3 weeks for each accident. And if that is 1 by 3, then your decay factor m is inverse of that. So m is 3. So once you have this, we can figure this out using P for probability, exp P for exponential, and then we have 2, and then we have m 3, and lower tail is false. So I was using this chapter number 5, and this one is try it 5.9. For A we used, so that's what gave us 0.423. So this was part A. And for B we use exponential, so PEXP 2. So this is where you have to be careful in exponential, because we are working with like mu and m, decay factor 1 by mu. Here we are not putting 1 by 3 because mu is 1 by 3. So we put reciprocal of that. So that is your m. Lower tail is false because we are interested in right tail. So 0.0024.